Hey Calculus, this is Mr. Aiden, and we are in a brand new unit, Unit 7, Differential Equations. When I was in college, I had an entire course on differential equations, and I loved it. If you know anything about me, I'm a chemist by nature, and so I love mathematics, dealing with chemistry, and so related rates just made calculus make sense to me, and DiffEq, differential equations, absolutely make calculus come alive for me. I loved DiffEq. And so we're going to start off step by step in this unit 7 of DiffEq, and we're going to start by taking a look at writing differential equations. Now, your big question right away is, what in the world is a differential equation? And in mathematics, what a differential equation is this. It's an equation that relates one or more functions and their derivatives. One or more function and their derivatives. And if you can see, like, take a look here. We have a differential equation right here. We have y prime prime plus y prime equals 2y. And so that is what's called a differential equation. We could write that a different way. We could write that as f prime prime of x plus f prime of x equals 2f of x. And so what that is the second derivative plus the first derivative of a function is equal to double the function. There's one more way we can write it, is in kind of Leibnizian notation, which is d squared y divided by dx squared plus dy over dx equals 2y. The second derivative plus the first derivative equals 2 times our function. And just like in a quadratic equation like this quadratic equation, y equals x squared plus 5x plus 6, we know what a quadratic equation is. So now we're trying to determine what is a differential equation. Well, there's solutions to this quadratic equation, isn't there? We can factor out y equals x plus 3 times x plus 2, which means x is equal to negative 3 and negative 2. Those are our solutions to our quadratic equation, which means there's also a solution to our differential equation. Let me give you an example. Let's say my solution would be y is equal to e to the negative 2x, which means what would y prime be if we did the derivative? We would have e to the negative 2x times the chain rule times negative 2, which means what would the second derivative be? The second derivative would be e to the negative 2x times the chain rule times the derivative. Negative 2 times negative 2 is positive 4. Now let's see if these work in our differential equation. Let's see if these are solutions. So we have 4e to the negative 2x, that's what the second derivative is, plus negative 2e to the negative 2x. 4e to the negative 2x minus 2e to the negative 2x is 2e to the negative 2x. Let's take a look. What's 2 times y? Y was e to the negative 2x. Does this equal each other? It sure does, which means this is a solution to my function, isn't it? This is a solution to my function. Well, what about this? Could e to the x be a solution? Because remember, in our quadratic, not only was negative 3 a solution, we plugged in negative 3 squared plus 5 times negative 3 plus 6, and we get 0. And then guess what? When we do negative 2, guess what happens when we put negative 2 in? We get 0 as well. These were both solutions. So could there be another solution for this differential equation? I don't know. Let's check. So let's take a look at the first derivative of this y2, which is e to the x. Let's take a look at this second derivative of y2, which is e to the x. And let's see if this works. The second derivative, which is e to the x, plus the first derivative, e to the x. Well, e to the x and e to the x is 2e to the x. Let's take a look. 2 times f of x, what was f of x, is e to the x. Did that work? That worked as well, which means we have two different types of solutions for this differential. Now let's take a look at writing a differential equation given a kind of a scenario. And so it says a particle is moving in a straight line. So we have a particle, that particle is moving in a straight line, and its speed, its magnitude of its velocity, is proportional to the square of the distance it has traveled. So it's proportional to the square of its distance. So its speed, or its magnitude of its velocity, is equal to the square of the distance. We're going to label distance as capital S. And we need to put a k in there because of our proportionality constant here. And so what do we know velocity is? Velocity is the rate of change of the distance with respect to time. And that equals ks squared. And that is what we call our differential equation. That is setting up our differential equation. And so you can see how what do we say is velocity equals the change of position with respect to time. Acceleration is the change of velocity with respect to time. And of course, speed is the change of distance. I'll put distance as a little s with respect to time right there. And so you can see this is how we set up what's called or write a differential equation. This shows up in AP Physics calculus all the time. Here we have a box. It's initially at rest, and we have this constant force F of A, and we have a frictional force that's working against it. And this frictional force, it says, is subject to the drag of the magnitude. So it's proportional to the magnitude of the velocity. So this frictional force is equal to kV. It's proportional to the magnitude of the velocity, which means as the velocity continues to increase, the force of friction is increasing proportionally. And it says, write but do not solve a differential equation to determine the speed of the box. Well, what do we know? In physics, we know the net force is equal to mass times acceleration. And what are the forces working upon this box? Well, we have Fa working for it, and we have the force of friction working against it. And this is how we set up what's called Newton's second law. Now we're going to set up our differential equation. We have mass times what is my acceleration in terms of velocity? Well, that would be dv over dt. That is called my differential equation. We have Fa, and what do we know Ff is? It's kV. And there is my differential equation to be able to solve for velocity. Now, we could write this differential equation with respect to solve for the position, and that would be m times d squared position over dt squared equals Fa minus k, and what is dv? Or sorry, what is velocity? Is dx over dt, and that would be my position function right there. Because acceleration is the second derivative with respect to the position, the velocity is the first derivative. So, but here, as this AP Physics C question is asking you for, is the acceleration is the change of the velocity with respect to time. And that is called setting up a differential equation. So it's a really good introduction to writing differential equations. I hope it helped. We're going to keep going more and more in depth on these diff EQs. Thanks, guys.